Engineering of Forces, Part 1. In these slides, we are talking about how mechanism of a number of forces when acting on an object behave, despite the fact of differences between these forces. There is one philosophy here. If there is no force, there is no motion. If there is no motion, there is no nature and being. So it means obviously force or forces are fundamentals of being in nature. Whether these forces are small forces between two electrons repelling each other, whether this force is something in which you push a trolley in a supermarket, whether the forces are attractions between galaxies in the universe, they all have the same mechanism and engineering despite their changes or differences in their behavior. Two types of forces. There are two types of forces in nature. One force, we call them in this category contact force. Contact force means if you push a wall, then definitely there must be a physical contact between your hand and the wall. Otherwise, the force cannot be accepted. There are many examples in real practice. Even, for example, once you have got the shoes and the floor, the weight is down, the reaction of the floor on the shoes is also an example of contact force. In contrast, non-contact forces, they do not need to be in contact, the two objects, like earth and mass, or any masses, or between any two objects, the gravitational force in nature. So it means, like here, these two masses, they do not need to be in contact with earth so that they can have weight. So they can be at any distance, not necessarily the contact. Another example is magnetism, north-south or south-north. If you have got a piece of metal, this piece of metal is attracted to the magnet despite the fact there is no contact between them, so at distance. Two forces. The mechanism and engineering of two forces. If two forces are acting on an object and if the object is in equilibrium, there are few simple physical properties in which these two forces must have. The two forces must be the same or equal numerically. If this is 10 Newton, this is 10 Newton. The two forces must be opposite to each other, otherwise the equilibrium cannot be achieved, and the two forces must lie on the same line. So it means in this diagram here, all the three elements satisfy. The two forces are opposite, equal, and then on the same line. In practice, not necessarily, for example, the line of forces in which both forces lie on must be always inside the object. It can be partially outside the object. Like this example, imagine you have got an arc of a metal, and this arc of metal is acted upon by two equal and opposite forces. So the line of force here you notice that is partially passing outside the object. Vector notation. So in terms of vector notation, simply here, the vector of F1 plus the vector of F2, if you add them algebraically, the sum is 0, which is a very simple equation. Three forces. Now, the mechanism of three forces acting on an object, we categorize this into two possibilities. One possibility is if all the three forces are parallel, like this example, in which these two forces are parallel to the third force, and this is in equilibrium, all the forces are in parallel, and if I draw a line which is perpendicular to all of them, or the extension of all of them, so all of them are perpendicular to this line. Obviously here, if for example F2 is more higher than F1, then F3 has to be more closer to F2. This can be taken also as a fact. Or the line can be, again, like our previous example, outside the object, like here. This is an arc of a metal, and this is F1, and this is F2, and this is F3. If F2 is more higher than F1, then certainly F3 has to be more closer to this side. And obviously, the extension or all the forces must be perpendicular to this line. Example, if this is a light beam supported by two supports, and if there is a load or an object of weight of F1 is more closer to the support, and obviously there are reactions from these supports in which we name them F2 and then F3. And then all of these forces now are parallel to each other, and then certainly F1 is more closer to F3 because F3 is higher than F2. Or if F1 is more closer to here, necessarily F3 will be higher than F2. Vector-wise, the vector summation of all of these forces in the format of vector must be equal to 0, in the same way as we had before for two forces. Non-parallel. So it means if the three forces acting on the object, they are not parallel. The rule is simple here. Imagine, for example, now you have got these three forces in which they are not parallel. The rule number one, so it means if you extend all of them, they all must meet at the same point. Either the point is inside the mass or the object, or maybe outside, like shortly we will have an example of that. And they form, or they must form, a triangle, which is called triangle of forces, head, tail, and closing like a loop. This is force 1, and then certainly here now this is force 2, parallelly. You now notice that this is parallelly shifted to here, and then finally here this is F3. And then if this is formed, then this is in equilibrium, or if this is in equilibrium, this triangle must be formed, vice versa. Now, a combination of this can be like F1, F2, F3, F1, F2, F3. Then another arrangement can also be possible, like F1, F3, F2, F1, F3, F2, and then obviously here these two are two different configurations here, but they provide the same physics. They are not different mathematically. Now the question is there any other arrangement? So I will leave it for yourself to look at it. Vector notation. So the same fact as we had in parallel, we still have got it here in vector format. The algebraic sum of all the vectors must be equal to 0. Now some examples to illustrate what we had previously. Imagine, for example, you have got an object attached to a string, and this object is pulled by a mass, by a force, and then obviously here the string will be inclined with the vertical by angle of theta. And if the object has got a weight, obviously here if this is in equilibrium, there must be a tension in the string. Then these three forces are non-parallel, and then from the previous rule they form a triangle of forces. Okay, this is your force F, and this is the weight, and this is the tension. This angle is phi as we have here. If you extend that, this will be by opposite, some simple geometry. Now, like in practice, imagine, for example, you have got a child, and this child is on a seat and attached to a rope. And then if this is held by a person in that direction, and this is the weight of the child, and this is the tension in this rope, in which if this is in equilibrium, for example, if this is standstill, they must form the triangle of forces. Another example, imagine that you have got a beam, and this beam here is attached to two strings, string 1 and string 2, with different angles, and then this is uniform. Obviously here these are two tensions coming from here, and this must pass through here. So all the three forces must meet at the same point. Then if this is tension 2 and if this is tension 1, then certainly here now triangle of forces can also be formed easily. Then to identify, so it means this is parallel to this is parallel to the weight, and this is parallel to that tension. Then working out the angles is fairly easy. So it means we can draw two lines horizontally here, and then using some simple geometry, if this angle is theta 2, and then this is 90 minus theta 2, which is exactly that angle. And the same thing here can be produced from here, from some simple geometry. And once you have got those angles, obviously you can have that angle, and then you can apply sine rule to work out those forces here. So it means if the weight is known, and if theta 1 is known, theta 2 is known, you can easily then calculate the tensions in those two strings using sine rule. Now results. Result number 1. If three different forces are acting on an object, and if the object is in equilibrium, and if two of these forces are parallel, then the third force must be also in parallel, but in this format here. So it means this is F1 and F2 are parallel, then obviously here the third force must also be parallel, in which certainly this is wrong, and must act in parallel and in opposite to the other two, so that to achieve the equilibrium. Now, triangle of forces here looks a little bit strange, although we still follow the formality. This is F1 and this is F2. Can you see the angle between F1 and F2 is 180 degrees? And obviously F3 has to act in opposite direction. So it means it must be on this line here. So it means you have got a triangle in which is made from three lines, but it is one line already. And the angle between this force and that is 0. This and that is also 0. Just for illustration, I did draw this line outside. The second example here, or the second result, if three parallel forces are acting on an object and they are not on the same line, it is then always the two outside forces must be in the same direction, and the inner one must be in opposite. So it means, if for example I have got three parallel forces acting on an object, okay, and then definitely here the two outside, this is going to be the inner one, the two outside must be in the same direction, the inner one must be opposite to them, otherwise the equilibrium cannot be achieved. For example, now here this is a wrong one. There is no way in which this can be possible to have an equilibrium, because this one is outside the two, is not in the inside one. So this is wrong and this is the right one. Four forces. In the four forces, this will be continued in our part 2 slides here. Thank you.